quite different problem, because we moved from the nuclear industry to the civil engineering world, because we are civil engineers. Then we deal with a very real problem, the problem of hydrogen embrittlement, a problem appearing in any environmental assisted cracking process because of the acidification and cathodization of the local environment in the close vicinity of the crack tip. This is a very special environment, producing hydrogen assisted cracking, even in prestressing steel wire. Then we are dealing with the role of the manufacturing conditions of the cold drawing conditions. My co-authors are again Miguel Lorenzo and Diego Vergara, and the audience is the same, but again emphasize my oldest university in Spain, and 2 years the anniversary. Please come to Salamanca in 2018. Beautiful place. I strongly recommend the visit, even from the touristic point of view. I am going to divide my presentation into only 4 parts: introduction, residual stress strain state after cold drawing, and hydrogen embrittlement susceptibility, and finally the conclusions. Let's go to the introduction. And cold drawing produces plastic strains which are not uniformly distributed, and also residual stresses which are not negligible. Then both fields of plastic strains and residual stress, hydrostatic residual stress, influence hydrogen embrittlement and can be the main cause of failure of prestressing steel in hydrogenated environments. We are in a structural integrity conference. Then the aims of the work are to analyze several variables of cold drawing of this manufacturing technique: the influence of hydrogen embrittlement susceptibility, of residual stress, the hydrostatic term, and cumulative plastic strain obtained after diverse drawing conditions. We are dealing with 4 key variables: the inlet diameter, alpha, the die bearing length, LZ, and we propose an innovative drawing procedure we have published in Engineering Failure Analysis after the Kazan conference, with varying diameter, alpha 1 and alpha 2, and the influence of the previous history of straining history in the material. Then the final aim is to estimate the optimal conditions for carrying out an industrial cold drawing process, even to improve it, commercial prestressing steel wires with improved performance from the structural integrity viewpoint. Then let's go to analyze the residual stress and strain state after cold drawing. Case of studies: inlet diameter, die bearing length, varying diameter, non-conventional, very innovative procedure, and the straining path. Then the first step of a real drawing chain, we use real data: initial diameter, typical hot roll bar of 12 millimeters of diameter, to a final diameter of 10.8 millimeters. Then, regarding the straining path, 2 real drawing chains undergoing different wide diameter reductions during drawing, with an initial diameter 12 to 7 millimeters in the commercial prestressing steel wire. For all the cases of study, these 4 variables, this is a summary of 4 previous papers. This is a review work, very difficult with this very quick Italian approach. I love this Italian approach, only 15 minutes, including discussion. Then these are the data from the materials: axisymmetric case due to revolutionary symmetry, isotropic hardening, and elastoplastic solid with 4 Mrs. yield stress and associated flow rule. We perform a finite element analysis of the drawing process. These are the data of the drawing, the conventional drawing, with inlet diameter alpha and bearing zone LZ. And we use different angles. First of all, the influence of the inlet die angle. We analyze 5, 7, and 9. Let's go to the results for the different die angles. Here we have the stress profile, the residual, the hydrostatic stress profile, and here we see at the surface of the wire, this is the wire axis, and this is the wire surface where hydrogen enters the material, and we have the following: the lower the inlet die angle, the lower the residual stress profile in the area of interest. Then, as soon as we see this plot, we should recommend lower angles. With regard to the stress, the situation is similar. For the lowest angle, we have the smaller profile of plastic strains. The main differences associated with the inlet diangles are located in the near surface area. In such a zone, the higher the inlet diangle, the higher the stress and strain fields. That's bad. Then, as a primary approach, we recommend lower angles. With regard to the die bearing length, we use 3 values. One conventional equal to the initial diameter, half of this value, and a quarter of this value. This is the reduction zone, AB, and BC, the bearing zone. Let's go to the effects. Then, the longer the bearing zone, the softer, the lower the hydrostatic stress profile, and also longer bearing zones produce, in this case, almost no effect. Then, if the bearing length is equal or higher than the wire radius, half of the wire diameter, no significant changes are produced in the residual stress and strain fields. If this bearing length is lower, this is not admissible, because in this case the hydrostatic stress linearly increases as the bearing length decreases, although only second order changes were found with regard to the strain fields. Let's go to this non-conventional, innovative drawing procedure with varying diameter. In this case, 2 zones, A' and A''B, main reduction zone, secondary reduction zone, and the bearing area, and 2 angles. We check in the analysis 2 possibilities. First angle 9 degrees to 5 degrees, and a softer drawing, a more careful drawing with 7 to 5 angles. In this case, the results are the following. Main differences associated with the inlet diangles are located in the near surface area. In such a zone, the higher the inlet diangle, the higher the stress. Very difficult to see here, a little bit higher for the square symbols. And of course, the strain, we have a peak for the longest primary angle, the highest primary angle with the same secondary angle. Non-conventional, innovative wire drawing with 2 angles. And finally, the straining history, a lot of information. I apologize, we don't focus in this such an amount of information. 2 real drawing chains with the same initial and final diameter, but different drawing steps. Wire A, heavy reduction at the first step, and softer later. You relax later. The second B is like a turtle, heavy reduction at the last step, because we deal with the main task at the end. Then, for heavy reduction at the first step, we have higher residual stresses in the area of interest. And for heavy reduction in the last step, we have lower tensile residual stresses in this area. With regard to the strains, they are higher for heavy reduction, black color, in the last step. Then, tensile stress distribution generated in wire B exhibit a higher gradient, inwards gradient for pumping hydrogen toward the inside part at the surface. While in wire A, the gradient, the inwards gradient of hydrostatic stress pumping hydrogen is negative. That's good. A heavy reduction at the first step produces a smooth profile of residual plastic strains than in wire B. Heavy reduction at the last step. And now, let's do the discussion about hydrogen embrittlement susceptibility. Again, the same equation, the audience is the same. At 10, fifth term, negative gradient of concentration, hydrogen is pumped by the positive gradient of hydrostatic stress, and a more complicated positive gradient of solubility, which itself is a one-to-one function of the plastic strain, concentration, hydrostatic stress, and plastic strain. And here, the full analysis, the complete analysis of all variables. With regard to the inlet diangle, optimal wire drawing, angle as low as possible. You see, the equilibrium hydrogen concentration is lower for the smaller angle. The available hydrogen at the wire surface is the lowest one, and the inwards gradient of plastic strain is negligible for the lowest angle. Wires drawn using higher angle exhibits a higher inwards gradient of hydrostatic stress acting against hydrogen diffusion towards the inner point. going quicker to the bearing length with no solid comments, we have the lowest concentration for the, at least this bearing length, half of the initial diameter. The optimal way drawing with a bearing length equal or higher than half of the diameter. With regard to the distributions, I think we have no time, and for bearing die angle, again we recommend an initial smaller angle at 7 degrees, lower concentration, but with the more intense angle, the higher angle in this non-conventional drawing with 2 angles. And finally, with regard to the straining path, we recommend, that would be surprising, lower equilibrium concentration for heavy reduction at the last step. For me, for my personal psychology, this is a surprise. Allowing the final task for the final stages of the drawing. Then, let's go to the conclusions. I think more or less on time. The optimal wire drawing consists of using a diameter as low as possible with a bearing length equal to or higher than the wire radius. If a low diameter is not possible, an alternative way for improving the structural integrity against hydrogen embrittlement is by using bearing die geometry with a secondary diameter as low as possible, and also the primary. The yielding history is a key issue in the generation of residual hydrostatic stress and plastic strain, since important changes are produced in the hydrostatic stress and equivalent plastic strain distribution. As a consequence, a careful design of the straining path, the straining history undergone during multi-pass drawing is advisable. And that's all. I finish with the logo of the University of Salamanca. Thank you very much for your kind attention.